about is is convection and radiation. And this is also known as heat loss. So, heat loss. Let's say you have a hot object, and let's just call it a pizza. So pizzas are generally red, and you just take it right out of the oven. And then you have a fan here. You have a fan, you have little fan blades here going around. You have some air coming in here. This fan is going to cool the pizza down. Okay. The fan has a temperature. You know, it's blowing the room temperature air, which we'll just call this TA is air. And this is the pizza temperature, so we'll call this T pizza. Okay. And the pizza has some area. We'll just call that AP. So if I want to tell you how fast is heat leaving this this pizza, well, you use the convection coefficient, because this is called convection. When heat loss is occurring due to motion of a fluid, which is in this case the fluid is air, over a hot or a surface of different temperature. So we relate the heat loss in this case to the convection coefficient, which is H, and this is very important. H times the area, again, because if you have a larger area, you automatically have a larger temperature difference, times the pizza temperature minus the TA, the air, so AP. And this would be the convection coefficient. If you, for example, if you're blowing with an even stronger fan, you would have a higher convection. If you're blowing with a lower speed fan, you would have a lower convection. If you were like running water past it, you would have a very, very high heat convection. This is why in cooling applications, where things are really hot, you run coolant, which is a liquid which is meant for cooling the specific piece of equipment. So another thing I wanted to discuss with regards to convection is something called natural convection. And this is sometimes more related to our discussion. Natural convection. And let me tell you about natural convection. First, we know that hot air rises and cold air sinks. So let's say you had your pizza again, and let's draw a side view of pizza. You know, if you look at the side of a pizza, it sort of looks like a rectangle, right? So here, so you have your pizza and it's steaming, right? It's steaming hot. Wow, I'm hungry. Lunchtime. Okay, so basically, essentially, what happens is that as this, you know, the hot air closer to the pizza, it wants to rise, and the cold air around the pizza, it's gonna want to sink down. So basically what this happens is hot air rises and cold air sinks down. It creates these sort of type of vortex circles. You may have seen this type of thing coming off your tea or coffee, like these type of circles. And the reason you can see it in tea and coffee is because it has water vapor. For example, if you put some colored smoke or colored air, you would be able to also tell this upon any hot object. So this type of this type of circular motion behavior is called natural convection, and it changes and it actually increases the amount of the convection coefficient. So there's something called the forced convection coefficient, and there's something called the natural convection coefficient. So these are two different things. Obviously, we would expect that the forced one would be higher because you're literally blowing air, but in the natural convection coefficient, well, it's called a capital N. These vortices forming due to the sinking of cold air, and the rising of hot air, this changes the convection coefficient. And depending on your geometry, you know, if you have a really long material, it'll change, because you'll have you know, this has to deal with Reynolds number and all these different types of heat transfer and fluid dynamics type of results. But let me just give you the brief summary so you can just remember. Natural convection will be different if you have, for example, your surface like this, standing straight up, and the vortices are forming on this side. So the heat will be the most. It'll be leaving the surface the most if you have your surface like this. If you have a bigger surface, this does change it to a certain extent. This does change the natural convection coefficient, just due to the interaction of the air with itself. If you have like a sort of like a flat plate, you know, like we had in the previous example, and this is all relative to gravity, because I said hot air rises and cold air sinks with regards to gravity. So gravity is actually pointing down here, so the Earth is beneath us, and that's pretty. Usually, it's a good assumption that the Earth is beneath you. Okay, so in this case, you'll have a convection coefficient here, and you'll have one on the side too, because the side is at a different orientation. The air leaving the hot surface on the side is going to be different depending on this height. It's also going to be the convection. You're going to have a different convection coefficient. It's going to have a different one on this side because it has a different length. And also on the bottom of this bottom surface, there's going to be a different convection coefficient. But what we're going to do, and this is just because the angle, the approach, you can imagine the vortices going on the bottom. You know, the air, the hot air is rising, and the cold air is sinking. So it's sort of going to have a different effect having it on the bottom or on the top. So this is something called natural convection. You can read more about it. But generally, sometimes what you want to do is just make assumptions and make the problem easier on yourself. In heat transfer class, you may be required to use some different experimental formulations in order to calculate the correct convection coefficient for each surface. But here, we'll sort of just use one. Just call it HN and assume it applies to all sides. And it'll get you in the right area where you need to. Usually this heat generation business it's maybe you'll get some inaccuracy here, but you want to get in the ballpark of knowing if your system is going to go to 100 degrees C or it's going to go to 50. That's something important. Whether it's 50 or 55 or 50 or 60, that's not as important actually. So now that we discussed convection, and this is the method of heat loss, we can also discuss radiation. And what is basically radiation? Radiation is a phenomenon in which a heated object releases light. Have you ever seen one of those thermal camera images? That's actually, there's a contraption in there, which we're going to go over, but it's a contraption in there that captures, that can sort of sense the light due to heating. But anyways, so heated objects release light. Just like when you see a fire, fires aren't red, not blue. When you see a fire, it sort of burns your skin. You could be standing all the way over here. The air from the fire to the person, you know, let's say there's like maybe 1 meter, or let's say this air is not going to get to you. You know, like you have one of those heated fans where the air is blowing toward you. You know, obviously the heated air is coming toward you, but where is the heated air transfer from the fire to you? Actually, the fire is so hot and it's releasing light, which is actually hitting your body, and that sort of, sometimes it feels like it's scalding, you know, burning your skin, so hot. But that's actually light that's actually coming out from the heated object. So, you know, human beings, they emit light because they're just hot, you know. I emit light because I'm hot, and, you know, you probably can't see it though unless you have a thermal camera. That's another discussion for another day. So this heated object releases light. So depending on how the differences between the object and the surroundings, the heat transfer is different. So first we're going to